Hey guys, today I would like to talk to you about the Bolzano Weierstrass Theorem. So the theorem states that every bounded sequence of a real number has a convergent subsequence. And the key word of this statement is bounded sequence and convergent subsequence. So let me elaborate on those. Let an be a bounded sequence. That is, there exists m in the reals with the absolute value of an less than or equal to m. Negative m less than or equal to an less than or equal to m. And in this case, negative m is a lower bound of the sequence an, and m is a upper bound of the sequence an. Then there exists a subsequence of an which converges. So let's do a quick proof of this. Consider the case of the limit supremum. So the proof states that negative m less than or equal to an is less than or equal to m. So all this is simply saying is any lower bound of the sequence is less than or equal to the sequence, and this is in turn less than or equal to any upper bound of the sequence. So how does the sequence relate to the supremum of the sequence? So the supremum of the sequence is the least upper bound. That means for any upper bound, the supremum is the lowest number. So given a sequence of upper bounds, the supremum has to be the lowest one in the set. So negative m, so any lower bound is less than or equal to the supremum of an, which is less than or equal to the upper bound, so any upper bound of an. Now here we are relating the limit supremum to the supremum of an because the limit supremum is a limit point. So the limit supremum has to be less than or equal to the supremum of the case of the sequence. So let's restating it. We have any lower bound is less than or equal to the limit supremum of an, which is less than or equal to the supremum of an, and this is in turn less than or equal to any upper bound of the sequence an. So the limit supremum is an element of the reals. We know that the limit supremum is a limit point for an, and the limit point is given L is a limit point of an if and only if some subsequence of an converges to L. So there exists a subsequence which converges to the limit supremum of an. This ends the proof for the limit supremum. Concerning the case of the limit infimum, the proof is exactly the same as limit infimum, except for this part right here, where you can see that in the case of the infimum and the limit infimum is actually greater than or equal to the infimum of an. So it actually states that for any lower bound of the sequence, the limit infimum is greater than or equal to that lower bound. But this also means that the limit infimum of an is greater than or equal to the infimum of that sequence. And of course, the upper bound is greater than or equal to all the other terms of the sequence. Likewise, the limit infimum of an is a real number. And we also know that the limit infimum is a limit point of an. So consequently, there exists a subsequence which converges to the limit infimum of an. So this ends that case. So let's consider the example. Considering the sequence negative 1 to the n, where n is 0, 1, 2, 3, 4, 5, so on and so forth. So we get the sequence 1, negative 1, 1, negative 1, 1, negative 1. And this you can obviously see oscillates between 1 and negative 1. So considering the case of the odd number for n. So when n is odd, it converges to negative 1. So we basically get the sequence negative 1, negative 1, negative 1, negative 1. So whenever n is odd, our y value is always negative 1. So the limit point for the subsequence when n is odd is negative 1. Considering the case of the even numbers for n, and in that case we get the sequence 1, 1, 1, 1, 1, and this you can obviously see converges to 1. So the limit point for the subsequence when n is even is 1. This sequence, putting both the subsequence together on the same axes, on the same graph, we get the bounded sequence. We get a sequence that is bounded between 1 and -1, and it gives an even. When n is even, we get 1, and when n is odd, we get a -1. So considering another example, this sequence I call an, and the sequence goes 1, 3, a half, 1.3, 1/3, 1.4, a quarter, 1.141, a fifth, 1.1415, so on and so forth. So taking the odd terms of the sequence, we get 1, 1/2, 1/3, 1/4, 1/5, 1/6. And as you can see, the numerator is always 1, but the denominator increases. So the sequence is basically 1 over n. And this, as the denominator grows, the sequence goes to 0. So the sequence converges to 0. And this, you can see, is clearly bounded between 0 and 1. So taking the even terms of the sequence, we get 3, 3.1, 3.14, 3.141, 3.1415, and this obviously goes on. This is not as clear, but this actually converges to pi, and this is also bounded. It's bounded between 3 and pi. So quick little background information on the theorem itself and the mathematicians behind the theorem. So the theorem is actually named after two mathematicians, Bernard Bolzano and Karl Weierstrass. Bolzano was a Bohemian mathematician, logician, philosopher, theologian, and Catholic priest. He was born in the year 1781 and died in the year 1848. Weierstrass, on the other hand, was a German mathematician. He is often cited as the father of modern analysis. He was born in the year 1815 and died in the year 1897.